These three objects sit in the same electric field between a cloud and the ground, but the field around each one looks completely different. And why? A wind turbine, a hot air balloon, and a swimming pool. All these objects somehow change the electric field between the cloud and the ground. And the reason why comes down to these three quantities: potential, field strength, and flux density. Let me show you how. We start by drawing the equipotential lines between the cloud and the ground. Each line sits at a potential. All along that line, the potential is the same, meaning that if we move a charge along the line, it's not going to gain any energy. But between the lines, there is a difference in energy. The first line sits at 300 kilovolt, the second line at 600 kilovolt, and the last line at 900 kilovolt. The electric field is perpendicular to the equipotential lines. Since there's no objects yet to disturb the electric field is the same from cloud to ground. What happens when we introduce objects in this landscape, such as a wind turbine, air balloon, and a pool? First, let's look at the equation that governs it. Let's start by introducing two charges of opposite polarity, a positive charge and a negative charge. These are the equipotential lines. Each sits at a different potential. The closer we are to the charge, the higher the potential. The field is strongest at the source and weakens with distance. Notice how the lines are close together near the charge and spread out further away. This is from the equation. It's the same voltage drop but a shorter distance, so the field is strongest closest to the charge. I place a sensor here. It shows the electric field strength at that exact point, and notice how it's perpendicular to the equipotential line and points from the high potential to the low potential. This is the equation made visible. So what is it actually showing us? Well, let's try to place some more charges and see what happens. You can see that the electric field strength increases, and also when we place the sensor, we can see that the potential near the charges are higher. So it shows us, first of all, the direction of the electric field strength, and also how strongly an electric charge would be pushed in this field. So this is what the equation actually can be used for. Or to say it in other words, how would the charge move in this field and how much energy would they gain? Let's get back to our example. First, we introduced the wind turbine. It's a grounded conductor connected to Earth, so its entire surface sits at 0 volt, same potential as the ground beneath. When I draw the equipotential lines back in, something immediately changes. Far to the right, the lines are evenly spaced as before, but near the turbine tip, the lines they crowd together. They have to because the tip is a conductor at 0 volt, so the lines must meet here perpendicularly. Still, the equipotential lines have the same voltage level, but what we see is that near the edge, near the tip of the windmill, the electric field strength crowds together over a small distance. And this is where the equation again becomes important. The voltage difference between the two lines is the same everywhere, but at the tip the distance is so tiny. It's the same voltage change, but a much smaller change in distance. And this is why the field strength increases dramatically. So if we write the equation for the one-dimensional case, this becomes even more clear. So it's the negative gradient of the difference in the voltage between 2 points over the difference in distance between these 2 points. If we draw this first for the orange equipotential line that sits at a higher voltage, we call that one V2. And then we draw it for a voltage that is at a lower potential, V1. And then we have the distance between these 2 points. So what we can see here is that if the voltage between these 2 points, if the voltage level between these 2 points is quite high, the difference is quite high, and that the distance is also quite low, then the electric field strength will be very high. But before I draw the pool, I need to show you one thing first, because what happens at the water surface? That's the whole point. When a field crosses from one material, as you can see here, to another, what actually happens to it? Does it change? Or how much and in what direction? The answer comes from Gauss's law. The total flux D through any closed surface is equal to the closed free charge inside of that surface. So what we do is that we place this pillbox here with a height h, and then we have the flux density coming out through each side of the box. The next thing we do is that we shrink the height, so the height h we shrink that to 0. And when that shrinks to 0, the sides disappear. Always say that they disappear. And the side flux vanishes. All that remains are the two flat faces sitting exactly on the boundary. And if there's no free charges on the surface, so no Q inside, then from the equation, we have that right-hand side is actually 0. And now, since the sides are shrinked to 0, we only have the normal component going through the boundary, which means that the flux density at each sides must be equal to each other. And this is what we have at the pool surface. Same flux density, but completely different field strength. Let me try to draw it here. First, we draw the pool, purple, or pool. And when I write the permittivity here, you can see that the permittivity for the pool is quite high at 81. And the permittivity for air is 1. So here we have a classic boundary condition between two different materials. And the pool actually bends, more like this. The pool actually bends the field lines because of the sharp edges, as you can see here. Inside the pool, I haven't drawn it, but the field lines are evenly spaced out. But something interesting happens inside the pool. And this is because of the relation between the flux density D and the electric field, as you can see here. So the flux density is equal to the permittivity times the electric field strength. And at the boundary, as we had from Gauss's law, we know that the flux density is equal across the boundary. And if we relate this to the electric field strength, then we can see that the electric field strength inside of the pool is actually decreased by a factor of 81. So the field inside of the pool is 1 over 81 times lower than outside of the pool. And this is an effect of the boundary conditions applied between two mediums. All right, but what about the last component, our air balloon? So this is my drawing of air balloon, the green one. And inside the air balloon, we have a conductor. That's the black one. This conductor could be the rail of the air balloon. And inside a conductor, there's no electric field because there are no free charges in the conductor. Any free electrons will redistribute themselves on the surface and cancel each other out. So there's no electric field inside of the conductor. And because the balloon is floating between two different potentials, between the orange one that sits at maybe 800 kilovolt and the red one that could be at 900 kilovolt, then the conducting rail would actually be at 850 kilovolt. So if you connect this to ground, some serious accidents could happen. That's it for this video. 3 objects, same field, and completely different physics. Thank you for watching.